Hello everyone, welcome to my video on limits at infinity and horizontal asymptotes. So let's take a look at a quick definition. Let f of x be the function defined for x on the interval from a to infinity. Then the limit as x approaches infinity of f of x is equal to L. This means that f of x gets arbitrarily close to L as x tends to infinity. So if we have our function here in green, we have our horizontal, essentially it's our horizontal asymptote, but right now let's just think of it as a limit. This limit here, let's put it as a solid line. So what we're essentially saying here is that when the x values get very large, the function just approaches this limit, this value over here on the y. Okay, so that's what we're telling. That's what we're saying. And limit as x approaches infinity, we're going in the positive direction. Same situation holds true for x's getting large in the negative direction. So if we go towards the left, our function could approach some limit L. Okay. So let's take a look at a couple of examples and see how this works. Okay, so before we look at an example, we need to know this theorem. So the theorem states that if r is just a positive rational number and c is a constant, then first we saw this in previous videos that the limit as x approaches 0 of c, some constant divided by x, is equal to plus minus infinity. This is essentially saying that if you're dividing by a very small number, depending on whether the constant on top is like a positive divided by a positive will turn it positive. If the constant on top is negative and the value on the bottom is negative, then negative divided by negative would be positive, positive, negative, 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 positive, negative. Okay, so you can get positive infinity or negative infinity. We saw this in a previous video, but the idea is if you're dividing by a very small number, it makes the whole value extremely large. Now we're looking at the other way. Case 2 is we're taking the limit as x approaches plus minus infinity. So you have a number on the numerator, and now you have x going to infinity on the denominator. It could have an exponent, it doesn't matter. But essentially what we're doing here is we're dividing by a very large number. So above here, we divided by a small number, which made the whole number big. Here, we're dividing by a very big number. So again, use your calculators to convince yourselves. Take any number on the top, like 5, and divide it by like a billion. You're going to get a number on your calculator that's 0.0000. Something that's essentially very close to 0. Okay, so this is another theorem that we have to keep in mind. I'm not going to prove it, I'm just going to state it. I think it's obvious. Now when you divide by a very large number, the whole number gets small. Okay, so keep this in mind. We're going to use this very often to solve problems with horizontal asymptotes. Okay, so let's take a look at some examples. Okay, so in this example here, our first example, it's asking us to find the HA, the horizontal asymptote. Okay, so how do we do that? So in order to find the horizontal asymptote, we're taking the limit as x tends to positive infinity and negative infinity. We want to know where this goes as x gets really large in the positive direction and very, let's say, large in the negative direction, or in a sense, very small. So to find the horizontal asymptote, it's always a good idea to have like an idea of what this function looks like. So e to the x, this is exponential in its basic form. So we should know, or the idea, the intuition you should have, not only the intuition, the function looks something like this. Now this gives us an intuition of what we expect our answer to be. So you should have an idea of what you expect the answer to be as x gets extremely large in the positive direction or extremely large in the negative direction. Okay. But let's go ahead and solve each. So let's take the limit. Let's go in the positive direction first. We're taking the limit as x goes to positive infinity of the function f of x, e to the x. So essentially what we're doing is direct substitution. You're taking the infinity and you're putting the exponent. So we're replacing our x with infinity. Now we have e to the infinity. Okay. E is just a number, 2.7 to the exponent infinity. So this just, everything's positive. 2.7 to the exponent infinity. The base is not smaller than 1, so this is going, it's bigger than 1. So it's just taken off to positive infinity. Okay. So essentially there's no horizontal asymptote as we get as x gets very large on the positive side, okay, as we would expect. It doesn't converge to a limit. If we take the limit as x goes to negative infinity, and we do the same thing, we substitute the x with negative infinity instead. What this gives us is e to the negative infinity. From laws of exponents, we know that if we have a negative exponent, that we could drop it, or essentially flip. Think of this as over 1, and flip it, we could drop it, giving us 1 over e to the infinity. And e to the infinity is infinity. E to a very large number is still a large number, and now we're doing 1 divided by a very large number. And as we saw in the theorem, the previous theorem, 1 divided by a very large number, or if we're dividing by a very large number, this thing here is extremely small. So you have to keep this in mind. This is very important. So it's essentially 0. It's not exactly 0, but it's so close to 0 that we accept it. We say that the limit is equal to 0. Okay. As we expect from our drawing. So our basic exponential function, e to the x, we know this is a horizontal asymptote. So it's never actually going to, this function is never actually going to go underneath the x-axis. Okay. So we have a horizontal asymptote at 0. This guy's never going to cross it. It's going to come very close, but it's never going to cross it. Okay. So that's for e to the x. So again, it's always a good idea to have an idea of what the function looks like. I think that helps a lot. And in this case, it's vital. So if you look at this function here, g of x is equal to arctan of x. Knowing what the function looks like is, I think it's the easiest way to figure out the solution to this, to find the horizontal asymptotes. Okay. So if we graph this, and we saw in a previous video what this looks like, because we dealt with tan. So if you know what tan looks like, you know what arctan looks like, because what you're doing is essentially taking the function and flipping it along the line y equals x. Okay, so it's essentially a mirrored image. So what we saw in a previous video, our tan function in green looks something like this. It's like a squiggly line goes through the origin, and there's asymptotes. There's horizontal asymptotes at negative pi over 2 and pi over 2, and this is periodic, so it repeats. The cycle repeats. So here we have the same idea, but now we're essentially flipping this image. So it's going to look something like this. And it's still, we're focusing just on one variation, which goes here and here. The one on top, same as over here, this was pi over 2, this is negative pi over 2. Same thing here. On top here, this is pi over 2. On the bottom here, this is negative pi over 2. So now we could see, just based off the function, knowing what the function looks like, which is again here in green, if we take the limit as x goes to negative infinity of arctan, let me write it this way, tan inverse of x. So substituting negative infinity into this might not help. Maybe if you plug it into the calculator, you'll start approaching values. But if you don't have a calculator, then you would have to know this by heart. So as x tends to negative infinity, here as x goes to negative infinity, the function approaches negative pi over 2. And similarly, the limit as x approaches positive infinity of arctan. So now if we go in the positive direction, the function approaches positive pi over 2. Okay. So we have a horizontal asymptote at negative pi over 2 and at positive pi over 2. Okay. So let's keep looking at some examples. Okay, so now I'm going to show you a nice trick to help you solve problems quickly. Just by looking at the function, if they ask you to find a horizontal asymptote, and a snap of a finger, within 2 seconds you'll know the answer. Okay, so this is a nice trick, but it only works for specific cases, so you have to be careful when to use this trick. If your teacher doesn't accept this trick, it's always good to have in the back, because you could anticipate what the answer is going to be before you solve it. I'll also show you how to solve it the proper way, which is slightly longer. Okay, so first of all, the trick only works when you're dealing with basically a rational function. So a polynomial function divided by a polynomial function. This is what we have here. F of x equals a1 times x to the n plus a2 times x to the n minus 1. So the n's are just constants. It's the highest exponent here. And each time the exponent is going down by 1, we have this word degree here. So the degree is the highest exponent. That's what we're talking about. So in this case, it's n, because this is n minus 1. So let's say this is 3, n minus 1 would be 2, and so on and so forth. So you're always looking at the highest exponent of the numerator and the denominator. And then on the bottom here, we have the denominator as well. The a1s, a2, all the way to the an's are just numbers, the coefficients, and same for the b's. b1, b2, bm minus 1, bm. They're just numbers, so don't let that intimidate you with the, this is just notation. So we basically have a polynomial divided by a polynomial, okay? So we have first case. So case 1, we have the degree of the numerator exceeds the degree of the denominator, okay? If this is the case, if the highest exponent on the numerator is bigger than the highest exponent on the denominator, then when we're trying to look for the horizontal asymptote, or essentially if we're taking the limit as x goes to plus minus infinity of the function, then it goes to plus minus infinity. Okay, so just by looking at the highest exponents, we know what the horizontal asymptote is going to be. And in this case, there's no horizontal asymptote, okay, because the limit goes to plus or minus infinity depending on the coefficients. Okay, so again, just looking at this example here, find the horizontal asymptote of this function here. Teacher asks you to find this. So what they like to do is they like to put things in different orders, so just be careful for that, don't fall for those traps. Just look at the highest exponent. So if you look at the numerator first, what's the highest exponent? The highest exponent is a 4. Okay. Look on the bottom. What's the highest exponent? Don't look at the coefficients, don't look at the numbers in front. What you're looking at is the exponent. So the exponent of the x here, we don't write it, but we know there's a 1, so that's smaller than 4. Here it's a 2, here it's a 3. So the highest exponent on the bottom is a 3. Since the exponent is higher on the numerator, this thing here, based off our case 1, has no technically I should write limit in front, but essentially this, let's put an arrow, this tends towards infinity. So this has no horizontal asymptotes. Okay. Essentially just by looking at the given function. Okay. So this is case 1, when the exponent of the numerator is bigger than the exponent of the denominator. Let's look at the other cases. Okay, so now in case 2, we have essentially that the degree of the numerator is smaller than the degree of the denominator. So if this is the case, if the highest exponent of the denominator is bigger than that of the numerator, then when you take the limit of the function, it's going to be equal to 0. This tells us that the horizontal asymptote is y equals 0. Okay. So in this example, find the horizontal asymptote of this function again. All we're doing is we're looking at the exponents. So looking at the exponents here, we have 5, 3, and 8. The biggest one is 8. So you're always looking at the biggest exponent. And on the bottom, we have 9, 2, and 0. So the highest exponent is at 9. So since the highest exponent is on the bottom, it's bigger on the bottom, this whole thing, when you're taking the limit as x goes to plus or minus infinity, it's going to always go to 0. So the horizontal asymptote here is y equals 0. I'm going to abbreviate it. Horizontal asymptote A is y equals 0. And just by looking at it. Okay. Let's look at the last case, case 3. Okay, so the third case, what we have is the degree of the numerator is equal to the degree of the denominator. Okay, so when the highest exponent of the numerator and the highest exponent of the denominator are the same, when we take the limit of the function, we get a1 over b1. In this case, what we mean by a1 over b1 is we're talking about the coefficients, the numbers in front. So when the highest exponent of the numerator is the same as the highest exponent of the denominator, then a1 over b1 is your horizontal asymptote. Okay. So if we look at this example over here, find the horizontal asymptote of this function g of x, which is equal to 6x squared minus 3x minus 4, all that over 8x minus 5 minus 3x squared. So what we do again is we look at the highest exponent. In this case, the highest exponent on the top is 2. Here they put it out of order, and just be careful, don't take the first 2 in front. The highest exponent here is a 2. So the horizontal asymptote is the coefficient in front of these two terms. Okay, so just be very careful. Here it's 6. On the bottom, if you're thinking 3, that's wrong. Take the sign in front. Don't forget the sign. So it's 6 over the coefficient here, the number is negative 3. So the horizontal asymptote is, let's write it down here, is y equals negative 2. Okay. So just by looking at this, we're able to tell what the horizontal asymptotes are. Okay, so this is a great trick. Keep it in the back of your mind when you're doing these types of problems. And now I'll continue to show you how to do this the proper way, the long way. Okay. Okay, so let's go ahead and do this example here where we have to evaluate the limit given it exists, where they give us the limit as x goes to infinity, and the function is x squared plus 3x minus 4 divided by 3x squared minus 8x plus 5. Again, pause the video, try it on your own, see if you get the answer. So based off what we saw, we know the answer. We should know the answer right away. Looking at the highest exponent at the top and the bottom, they're equal, so the answer is the coefficient. The coefficient of the x squared on the numerator is 1. The coefficient of the denominator x squared is a 3. So the answer here we expect is 1/3. Okay. How do we solve this properly? How do we do this the proper way? Why is this true? So essentially to solve these, the trick is the same. You're always going to, there's two ways of doing it. You could either factor or divide. So let's put this in the bubble. Divide, I'll show you the division way. Divide by the highest exponent of the denominator. This usually gets the trick done. So let's put this in a bubble, keep this in mind. So you're either dividing by the highest exponent of the denominator, it's always the denominator we're working on, or you could think of it as factoring it out as well. Both ways are fine. I'm just going to divide. So basically the degree of the denominator, or the highest exponent of the denominator is what in this case? Well, it's an x squared. So what we're going to do is we're going to divide the top and the bottom by x squared. Okay, that's step 1. So this we're going to rewrite it as the limit as x goes to infinity of x squared plus 3x minus 4, all that divided by x squared, big division sign, 3x squared minus 8x plus 5, all that divided by x squared. Okay, let's continue here. So notice that I'm always writing the limit sign in the front. This is important. Do not stop writing the limit until you actually use it. And what we're going to do is divide each term individually. So focus on the numerator here, this fraction on the top, and we'll divide. What's x squared divided by x squared? So you're dividing each term individually. Think of this as fractions. Oops. We're allowed to do this. Like if you have 1 plus 3 plus 4 divided by 2, we could rewrite this as 1 over 2 plus 3 over 2 plus 4 over 2, and deal with each term individually. That's what we're going to do here. Okay. So x squared over x squared, I'm just going to write it as 1. Here we have 3x over x squared, which simplifies to 3 over x. Okay. So you have to remember your laws of exponent, 3x over x squared. This is x to the 1, the coefficient is a 3. 1 minus 2 is x to the negative 1. You're subtracting the exponents because you're dividing the same base, laws of exponents. So 1 minus 2 is negative 1. And then you redrop negative exponents, you drop it back down. So 3 over x. Okay. Or in a sense, you could think of it as 3x over x squared. And x squared is x times x, right? And one of the x's cancel. So you're left with 3 over x. Both ways are fine. Okay, so that's how we get 3 over x. Same argument over here, we have negative 4 over x squared. That stays the same, negative 4 over x squared. And now we do the same on the bottom. Okay, so 3x squared over x squared is 3. 8x over x squared is negative 8 over x. Again, one of the x's cancel. And then lastly, we have 5 over x squared. So plus 5 over x squared. Okay. So we have it in this form. Why do we want it in this form? The reason why we want it in this form is because we want to use the theorem that we saw earlier in the video. The fact that when you're taking the limit as x approaches infinity of any number, I think I could use the letter c, over x, and the x could have an exponent, like here there's an x, here it has an exponent too, it doesn't matter, this thing here always goes to 0. And this is the property that we're using. Okay, so when we divide by a very big number, the whole thing gets small. Now this is where we apply it. So let me keep this on the bottom. Here we have to be careful with notation. So what we're going to do is this limit over here that we're taking in front, we're going to tackle all the terms. Okay, so we have to write limit in front of all of the terms. So this is just a bit tedious, but we're going to write it out. So limit as x approaches infinity of 1 plus limit as x approaches infinity of 3 over x minus the limit as x approaches infinity of 4 over x squared. All this over, so I'm taking the limit of each term. The limit as x approaches infinity of 3 minus the limit as x approaches infinity of 8 over x, and then finally the limit as x approaches infinity of 5 over x squared. Okay, and now we use this property. The limit as x approaches infinity of 1, well, x is going to infinity, but there's no x here. So the answer here is just 1. Over here, we're taking the limit as x goes to infinity of 3 over x. So the denominator is going to infinity. Any number divided by infinity. So when you divide by a very large number, the whole thing goes to 0 by this property here. Okay. Same thing here. 4 divided by infinity squared. We're dividing by a very large number. Again, the whole thing goes to 0. So this goes to 0. And using the same argument on the bottom, so we have plus 0, minus 0. And on top here, the limit as x goes to infinity. Let's start off with the 3. Then 8 over infinity is 0. So this thing goes to 0, so minus 0. And 5 over infinity squared is going to 0. So we're left with 1 on the numerator, 3 on the denominator, as expected. And this turns out to also be the horizontal asymptote. But in this case here, they didn't ask for the horizontal asymptote, they just said to evaluate the limit, which is essentially as x goes to infinity, which is essentially the same thing. Okay, so I hope this helped. Let's keep practicing and look at different examples. So in this example here, we have a small curveball that's thrown at us. Again, I urge you guys to try it on your own. So the first thing you have to catch is that the limit is x as it approaches negative infinity. And the other thing is that we have ln sitting in front. So we no longer have a polynomial divided by a polynomial. Okay, but one of the nice properties of limits is that when we have a continuous function sitting in front, we could take the limit and jump inside. Okay, so we'll essentially ignore the ln and jump inside and take the limit of what's inside the ln. So this is equivalent to ln of, and let's take the limit inside, of 16 plus x squared over x squared plus 4. Okay. So in the previous example, I showed you guys divide by the highest exponent of the denominator. In this case here, again, we should know what the answer is. We have the highest exponent is x squared, the highest exponent on the bottom is x squared. They're the same, so the answer is the coefficients in front. It's 1 over 1. We expect it to be 1 to evaluate this. But let's go ahead and do it the proper way. But instead of dividing by the highest exponent, let me just show you the same technique, but with factoring instead. So let's go ahead and factor by the highest degree of the denominator. So ln in the front, I'll keep the limit here as x goes to infinity. And the highest degree on the denominator is x squared. So I'm going to factor out an x squared on the top, and I'm going to factor out an x squared on the bottom. Doesn't matter which method you use, both are equivalent. If you want to divide by x squared on the top and bottom, you can do that as well. So factoring it out, we get x squared. And what we're left with is 16 over x squared plus 1. All that divided by x squared, which is factored out, 1 plus 4 over x squared. Okay. So it's a bit weird, but at the end of the day, if you don't believe me, what you should do is multiply the x squared back in and see if you get back what you started. So if I distribute the x squared back in, x squared times 1, that gives me my x squared, and x squared times 4 divided by x squared, well, the x squareds are going to cancel, you're going to be left with 4. Okay, so just to double check your answer, distribute whatever you factored out. Okay. So now that we did this, notice that the x squareds cancel, and we're left with this. So we have still the ln in the front, and now we're going to take the limit of each term, giving us limit as x approaches infinity of 16 over x squared, plus limit as x approaches infinity of 1, all this divided by limit as x approaches infinity of 1, plus the limit as x approaches infinity of 4 over x squared. Using our theorem, we know that the first term here, limit as x approaches infinity of 16 over x squared, we're dividing by infinity squared. So any number divided by something that's very large goes to 0. So we're applying that theorem again. Limit as x goes to infinity of 1. The x is going to infinity, there's no x, so it's just the identity, just 1. Here, same thing, just 1. And then here, it's the limit as x approaches infinity of 4 over x squared, same reasoning. We're dividing by infinity squared, so that whole thing's going to 0. Oh, sorry, not infinity. All these are minus infinities. My apologies. Negative infinity. Okay, I'm happy I got that. So it's not infinity, it's negative infinity. We have to be careful. Okay. But the same reasoning applies because when you're dividing over here, negative infinity squared comes back to be positive. So in the end of the day, it didn't hurt my result. It's the same conclusion, but I had to put the negative in front. That's a mistake on my part. Okay, so we still end up getting ln of this is 0, this is 1, and on the bottom we have 1 plus 0, which is just 1. So we get ln of 1, which we saw in a previous video. Ln of 1 is 0. And this is the answer. Okay. So let's keep practicing. Okay, so in this example here, we're asked again to find to evaluate the limit. We have the limit as x approaches positive infinity. Now we have the square root of x squared minus 8x minus 8 minus x on the outside. Okay, so what's different about this example here is 1, we have a square root, 2, we don't have a fraction. All the examples we've seen previously always dealt with a fraction, and we're looking for the highest exponent of the denominator. In this case, we don't have that. So a common trick that shows up, and typically when you see square roots, one of your first instincts should be to multiply by the conjugate. So let's look at one of those examples. So the conjugate, what it is, you're essentially multiplying this whole thing by 1 in a fancy way. The way is specifically, you take exactly what's here, keep it the same, and just switch the sign of the two terms. So the first term here is with the square root, keep it as is. Here it's minus x, that minus turns into a positive x. Okay. So multiplying by this is changing the function, so we can't do that. So what we have to do is cleverly divide by the same thing. X squared minus 8x minus 8 plus x. So we all agree that what I multiplied by here and divided by it, it's the same thing. So anything divided by itself is 1. So it's just a fancy way of multiplying 1 and not actually changing the function that we're working with. Okay, so keep that in mind. And now what we're going to do is multiply the numerator. Leave the denominator as is. So we have the limit as x approaches infinity, so keep writing the limit in front. And this is two terms. We have the first term, second term, first term, second term. So we're essentially foiling. We're going to FOIL. Multiply the first term by the second term. Remember that the square root of x times the square root of x is just x. These square roots cancel each other. So the first term is essentially just x squared minus 8x minus 8, right? Because the square roots cancel each other. Whatever's in the inside is the same. So the square roots are gone. Another way you could think of this is square root is really just a half. And a half, whenever you're multiplying the same base, you could just add the exponents. So a half plus a half is a whole. So it's x to the 1. It's the same thing. And that's what we're doing here. So whatever's inside the exponent, inside the roots, essentially just recopy it. And then the next term is the first term here multiplied by the outer term here, giving us, let me write it out, plus x times the square root of x squared minus 8x minus 8. And then we're doing the outer, so negative x times square root of x squared minus 8x minus 8. Okay. And then negative x times x gives us minus x squared. Okay. Whenever you multiply by the conjugate, this is always going to occur where the two middle terms are going to cancel. It works out this way because we're essentially doing completing the squares. No, not completing the squares. We're doing difference of squares backwards. So we have x squared. Let me just rewrite the denominator plus x. So this term here is always going to cancel this term when you complete the squares. Okay, because it's the same number, just one's positive, one's negative. Okay, so those guys are gone. And on top of it, this guy's gone. Negative x squared cancels out with the positive x squared from the beginning. So what we're left with is the limit as x approaches infinity, negative 8x minus 8. Everything else canceled on the top, and on the bottom we have square root of x squared minus 8x minus 8 plus x. Okay. So at least now we have our fraction. It's not polynomials, but at least we have a fraction. So we can divide by the highest degree of the denominator. You have to figure out what the highest degree of the denominator is. What's the highest exponent? I shouldn't say highest degree, I should say degree. But what's the highest exponent? Well, if we think of the first term, x squared being the largest, it's inside the square root. So the square root of x squared is just x. So we could conclude that the highest exponent on the denominator is just x. So let's go ahead and do that. So keep in mind, square root of x squared is x. Okay. So if we divide the top and the bottom by x, excuse me, we get the limit as x goes to infinity of negative 8x minus 8 over x over square root x squared minus 8x minus 8 plus x over x. Okay. So let me just erase the top to give myself some room. This gives us, here we get negative 8 minus 8 over x. I should be writing the limit on each term, but just because I'm running out of space, I won't do that. But what's important is this next step over here. So we have the square root of x squared minus 8x minus 8, all that in the root, divided by x, right? Because we're going to divide by x on both terms. But we agreed that x is the same thing as the square root of x squared. So instead of dividing by x, I'm going to divide it by the square root of x squared. Okay, and I'm going to put everything inside the root. And here x divided by x is 1. Okay, so let me just continue here on top. This gives us the limit as x approaches infinity, negative 8 minus 8 over x. This is a non-issue, we know how to deal with that from our theorem. And here we can rewrite everything as inside one big square root. So whenever you have the division of square roots, you can put them all into the same root. Okay, so we'll go ahead and do that. And we're going to divide them at the same time. So x squared divided by x squared is 1. Negative 8x over x squared is negative 8 over x. And here negative 8 over x squared is minus 8 over x squared. Okay, plus 1. So what we see here is that when we take the limit, this thing here, 8 over x goes to 0 because we're dividing by x, which is going to infinity. So that's 0. Over here, 8 over x goes to 0. We're taking the limit of this term as well. That goes to 0. And we're taking the limit of this term here, which goes to 0 as well. So I skipped a couple of steps, but the details that I'm skipping is essentially the fact that the limit is attacking each term. So really I should be writing that out. I just don't have space, so I'm not doing it here. And the other thing is the limit jumped inside the square root. But again, this is fine. Like we saw with the ln in the previous example, the square root's a continuous function, so the limit could go inside the root. There's no issues there. Okay. So these guys go to 0. So what we're left with is on the numerator, negative 8. On the denominator, we have 1. inside the square root, so square root of 1 plus 1. This is negative 8 over square root of 1 is 1, 1 plus 1 is 2, giving us a final answer of negative 4. And that's our answer. So I hope this helped. Let's take a look at one final difficult example. Okay, so in this example here, we're asked to evaluate the limit. Here, we're specifically asked to find the horizontal asymptote of this function over here. And at the same time, you could try finding the limit as x approaches negative infinity of cos of x cubed. So before we get to E, let's start off with D. We have to find the horizontal asymptote. So looking for the horizontal asymptote, we're really asked to find the limit as x approaches plus minus infinity. We want to know as x gets really large from the right and x gets really large from the left side, what's happening to this function. So the first thing you have to catch, and you have to be very careful, is that our trick doesn't work here. Not quite, because in order to use our trick from before is that we need a polynomial divided by a polynomial. These are exponentials. Okay. But the nice thing is that our trick still actually works. You can still use it in a sense. Okay, we just have to be a bit careful. So let's start off by finding the limit as x goes to infinity of f of x, which is 6e to the 2x plus 4e to the x minus 2022 over 3e to the 2x plus 2e to the x minus 1. So when we take the limit as x goes to infinity, what happens? So we could plug in infinity with our x's, but all we're going to end up getting is infinity over infinity, which is an indeterminate form. We don't know how to deal with this yet. Okay, later on in the semester we'll see something called L'Hopital's rule, which we'll know how to do that. But in this case, we can use the same trick from over here. But instead of dividing by the highest exponent, we're going to divide by the term that goes to infinity fastest. So we have e to the 2x, e to the x, and then nothing. Essentially, the e to 2x goes to infinity fastest. So we could divide or factor out the e to the 2x. That's the game plan here. Okay, so this is equal to the limit as x goes to infinity of, let's write it out, 6e to the 2x plus 4e to the x minus 2022, all this over e to the 2x, divided by 3e to the 2x plus e to the x, plus 2e to the x minus 1, all this over e to the 2x. And what we get is limit as x goes to infinity. On the top here we get 6, the e to the 2x is cancelled. Here we get plus 4e to the x, 4 divided by e to the x, and then minus 2022 over e to the 2x. And on the bottom, what we get is 3, because e to the 2x cancels out with e to the 2x. 2e to the x over e to the 2x is plus 2 over e to the x. Essentially, they're the same base, so you could just subtract the exponents. That's how we're getting the answer here, similar to what we saw earlier, because e to the x divided by e to the 2x is the same thing as e to the x. Laws of exponents, same base, subtract the exponents. X minus 2x is e to the negative x, which is just 1 over e to the x. Okay, so that's how we get the e to the x on the bottom here. And then we still have the coefficient too. Okay, and then lastly we have minus 1 over e to the 2x. And from this, we're able to solve. Because now if we take the limit, we still use our property. It looks different, but it's the same concept. 6 plus, the 6 is fine. When we take the limit as x approaches infinity of this term, the 4 over e to the x, well, e to the infinity, we saw earlier, is infinity. So we have 4 divided by infinity. So again, we're dividing by a very large number, which comes out to, dividing by a very large number makes the whole number smaller, essentially 0. So close to 0 that we accept it to be 0. And same here, negative 2022 divided by e to the 2x, well, this thing's going to infinity. E to the infinity is again infinity, and we're dividing by infinity. We're dividing by a very small number. Sorry, by a very large number, which is making the whole number small. So this goes to 0. And we use the same arguments down here. This goes to 0, and this goes to 0. Leaving us with 6 on top, 3 on the bottom. So 6 divided by 3, the answer is 2. Okay. So that's the positive case. Since they're asking for a horizontal asymptote, so as x gets very large on the positive side, it's going to converge, or the limit's going to be 2. So the horizontal asymptote right now is 2. But you have to see what's happening on the left side. Okay, so let's go ahead and check the left side as x goes towards negative infinity. To save on time, and because I don't have space, I'm just going to put a minus inside, because we're essentially following the same steps. Minus infinity, now we're going to go here, minus infinity. We still divide by the highest exponent, the term that goes to infinity the quickest, we're going to divide by that. And we come down to this stage here. But now we just have a negative in front. So remember, horizontal asymptotes, you have to check the positive case and the negative case. Okay, and now we're at this stage here, so this doesn't go to 0 anymore. Actually, let's rewrite this. I think it's be easier if we just rewrite it. This case over here, if it goes to negative infinity, what we could do is direct substitute and plug in the negative infinity. This gives us 6e to the negative 2, right? 2 times infinity, or I should say negative infinity. If you substitute the x with negative infinity, 2 times negative infinity is still negative infinity. So we get e to the negative infinity plus, again, we substitute here with negative infinity, we get 4 e to the negative infinity minus 2022. All this divided by, so I'm essentially just substituting the value in e to the negative infinity plus 2 e to the negative infinity minus 1. Okay. And remember, e to the negative infinity, this is just side work. We have a negative exponent, so it's essentially dropping the e. It's on the denominator. And e to the infinity, we said before, was infinity. And 1 divided by infinity, we saw, dividing by a very big number makes the whole thing smaller. This goes to 0. So e to the negative infinity is essentially 0. So this goes to 0, this goes to 0, this goes to 0, and this goes to 0. Leaving us with, what's this? Negative 20, 22 over negative 1, which is just 20, 22. And that's the answer. Yeah, so the horizontal asymptote as x approaches positive infinity was 2, and the horizontal asymptote as x goes towards negative infinity is 20, 22. Okay. Now for the final example, the limit as x approaches negative infinity of cos x cubed. Let's erase this. For e now, let's try direct substitution. So if we substitute the x with negative infinity and x cubed, we get cos of negative infinity cubed. Negative infinity cubed is negative infinity times negative infinity times negative infinity. We're multiplying by negative infinity 3 times. So we have cos of essentially negative infinity. Okay. So this is a bit of a trick question. And in order to answer it, we have to know what the cos function looks like. So keep in mind the cos function, cosine, those functions we should know how to sketch. But essentially, let me do it in green. It's a function that oscillates between negative 1 and 1 forever. We're going in the negative direction. The highest point is 1. Oh, sorry, this is a sine function. Cos has its max at 1, so let me redraw this. Okay, that's better. Now it's a cos function because it hits a max of 1, and this is negative 1. But essentially what you have to know about cos is that as x gets very large to the right or very large to the left, it's always stuck between negative 1 and 1. So what's the limit? So this is a case where we would say the limit does not exist. Okay. So that was a bit of a trick question. Okay, so I hope this helped. Keep working hard, and I'll see you in the next video.